All right, guys, these are the Chapter 8 notes. This chapter is on linear regression models. So what is a linear regression model? So a linear regression model is the line of best fit, and we use these models to predict an output value or a y value for a given x value or input value. So if we know the equation of the line of best fit for boys' height and shoe sizes in AP Stats class, we can use the equation to predict the shoe size of a boy who's 71 inches tall. All right, so these are models, and that is why we use that y hat, because it's a predictor, it's not a guarantee. So just like we use p hat for the sample, we use y hat for a linear regression model. All right, so the first vocab word is a model, and it is an equation or formula that simplifies and represents reality. So an equation that represents a real situation. I like to try to put things in my own words when they make more sense. Okay, so linear model. A linear model is an equation of a line and to interpret a linear model, we need to know how the variables, know the variables along with their units. So need to know what x and y represent with their units. A predicted value, that is our y hat value. So we use these models to predict. And so it says the value of y hat found for a given x value. All right, residuals. So a residual is like an error. It's how much off the line of fit you are. So it's the difference between the predicted value and the actual y value. Another way to think of it is how far off the line of fit you are. There's an equation for it, so I'm going to do that down here to find your residuals. They don't call it R because they use R for the correlation. So they actually call it E for error. So E equals y minus y hat. So let's talk about that for just a second. So let's just say that we're on, here's our line of fit, and we're right above or below, or maybe even on the line of fit, right? So the difference from your observed minus your expected. So E is the observed minus the expected. So if you're up here, right, here's your observed y. The corresponding y hat, remember your x value has to be, like here's your x-axis, right? So let's say we put in x is, I don't know, 2 or something. And we plug it into our equation, we'll get this value. This is our y hat value. And so the difference from here to here is obviously positive. However, let's say that this were, right, 3, and we're looking at this y value. Well, now the difference from here to here, right, we would be at y, and then here's y hat. Y hat is always on the line. This would be a negative value because y hat would be larger. And so you can be below the line of fit or above the line of fit. And so you can either have a positive residual, a negative residual, or if you're on the line of fit, then you would not have a residual. Okay, least squares. So they also call the line of fit, I'm going to put in least squares, regression line. Another way to say it is the line of best fit or line of fit. And so the least squares is it's a criterion that specifies the unique line that minimizes the variance of the residuals. Okay, so it's a unique line. The least squares regression line, there's a way you find it, right? It's not just by sketching it in, your calculator finds it, but it's the line, I should say the equation of the line, that minimizes every residual value. The best way to show this is using technology, and unfortunately I'm not going to be in the position to sit down with you guys and show you an equation of the line of fit program unless we meet for a Zoom meeting. So we may do that, but I'm going to give you a picture from the book that kind of helps you to visualize what's happening with that line of fit. So let me see where it is. I don't think they talk about it here. No, they don't have a nice picture of it. And so what I'm going to do is we will meet in a Zoom meeting so that I can show you what they mean by a least squares regression line, because there's some really cool programs that will show you different lines and how the squares that are built around them. Like if you look at down here, if you look at this like square that you could build, and then you look at this square that you could build, and this one there would be no square. This one, right, it would look something like this. And what happens is that your calculator or that any program will automatically find the line that makes these squares the smallest squares possible. That's why it's called the least squares regression line. Regression to the mean, it says because the correlation is always less than 1, each predicted y hat tends to be fewer standard deviations from its mean than its corresponding x was from its mean. It's called regression to the mean. I've really never seen that brought up before on an AP exam, but I'm going to go ahead and write it down. So each predicted y hat tends to be fewer standard deviations from its mean than its corresponding x was from its mean. So let me see how I could explain that, maybe using some of the homework from yesterday or the other day. Okay, so I standardized each value of the heights and the shoe sizes. Remember the heights, which are in purple, those were our x values, and these are our corresponding y values. And so what they're saying here is if you were to look at this value, it says every y hat, right, every predicted y hat tends to be fewer standard deviations away from its mean than the corresponding x value. So basically what they're saying is for the most part, and I said tends to be, right, the y values will be closer to the mean right here than the corresponding x value was. And you can see that both in the calculation and also in the numerators. All right. Tends to be, you notice that this one isn't necessarily true, but they're saying it tends to happen. Okay. The regression line, or the line of best fit, it's also called a least squares regression line, and it is a model for the particular linear equation. So the model for a particular linear equation. And it satisfies the least squares regression, but we usually just call it the line of fit, so that each least squares is minimized. So that all of these areas are minimized. And the equation is y hat equals a plus bx in our calculator. Now, in the book and also on the AP exam, they will use another equation, which is y hat equals b naught, or b0, that's our y-intercept where x is 0, plus b1x. So you need to be familiar with both. Oh, I hope I'm not going off the screen. I am a little bit. There we go. Okay. And so we're going to see in just a minute that this is the one that we'll use more often. This only shows up in our calculator. Again, this one is the calculator speak, but this is the one that we will be using in today's lecture. Okay, so the slope, B1, I'm going to put that right here so that we don't forget. B1 is the slope. The slope gives us the value of y units per x units. We always interpret it as y units per x units. And so generally we have a slope, B1, that's a decimal over 1. And so generally x is 1 unit. And the way that we calculate that value is B1 equals R times S sub y over S sub x. So remember, S sub y is the standard deviation of y, and S sub x is the standard deviation of x, and R is the correlation coefficient. Okay, the y-intercept, which we call B0, whoops, I want to change colors. Sorry, hold on. So let me change colors here. So the y-intercept, which is B0, it is the starting value in y units. So it's the y hat value when x is 0. And of course, you can find it in this equation by just moving the bx over. And so the equation for this is y, why would I put y? Duh, my bad. B0 equals, so if I move this bx over to the other side, it would be y hat minus b1x. And the standard deviation of the residuals, and so we call that the standard error of the residuals. So the standard deviation of the residuals, standard deviation of residuals. It's also called the standard error of the residuals. And the equation is given by S sub E equals square root. The errors, oh goodness, my bad. That doesn't even look like anything, sorry. The sum of the errors squared over n minus 2. So the sum of the errors squared, I don't like my sum. Hold on, let me fix it. The sum of the errors squared over n minus 2. So if you think about it, like when we would do standard deviation, it's similar. We find the differences, right? The x minus the mean over the standard deviation. Well, each error, you're doing that x minus the mean or predicted, observed minus expected. And then we square each of those values, which is why we're squaring the values. And then instead of dividing by n minus 1, we divide by n minus 2. And we do that because we have two variables, so x and y. All right, r squared, it's called the coefficient of determination. So this is the coefficient of determination. It's an overall measure of how successful the regression is in linearly relating y to x. So one way to put it is an overall measure of how successful the regression is in relating y to x. Another way to put it, I'm going to have to go down here. I don't have enough room, so I'm going to go down here. Another piece of information about it, it's the fraction or the percent of the variability of y that can be accounted for by the regression on x. The fraction or percent of the variability in y that can be attributed to the regression on x, or the variability in, to x. Our book says it this way. I don't really like it, so I use a little bit different interpretation. It's also the square. It's literally the square of the correlation. R. That's why it's called R squared. So my interpretation, the one I've seen that's a little bit better than this is the fraction or the percent of the variability in y that can be attributed to, I have heard it said, the variability in x. So I'll generally say it that way. All right, let's move on. That's all the vocab, guys. Okay, example. AP Stats, boys' height and shoe size. So it says find the equation of the line of best fit by hand. Compare it to the linear regression equation found using technology. All right, so the first thing I need to do is I'm going to go back and look at my information from last chapter, right? So we had this set of data, and we're going to be finding A and B by hand, and we'll also find them by technology. So I'm going to write down the equation of the line of fit. So the line of fit is y hat equals B0 plus B1x. And I want to remind you that B0 and A are the same thing. and that B1 and B are the same thing. So looking back at how to find the value of B1, if we look back in the notes from just a minute ago, we can see that B1 is equal to R times S sub Y over S sub X. So B1 is equal to R times S sub Y over S sub X. And it just so happens that I have that handy dandy information right here in my calculator. So let me look at, if you didn't already put your data in a list. So list 1 was my height, list 2 was my shoe size. Now I want to look at S sub Y and S sub X. So I'm going to go ahead and write down my S sub X, which was 2.46. I'm going to go many decimal places. It goes 7, 9, I'll go to 8. And then S sub Y was 1.26954. All right, so that's our S sub Y and S sub X. Now R, we already hand calculated it from last homework, but if you've forgotten to find your R value, you go to Stat, Calc, LinReg number 8, right? It's going to give you your A and your BX, your A and your B, but we want to do it by hand. So R was 0.7326. And I'm going to use this to calculate my line of fit slope. So B1 equals R, which is 0.73262 times S sub Y 1.26954 over S sub X 2.46798. I'll go ahead and multiply and divide that. So 0.73262 times 1.26954 divided by 2.46798. And I get that B1 is 0.376, and I'm going to round it to a 9 right there. All right, then to find B0, if we look back at our notes on how to find B0, B0 is the Y value when X is 0. So I am going to substitute in 0 to find my Y value, my B0 value, or I'm going to pause right here actually, guys, because we're getting kind of long and it takes a while to upload. Okay, we're at 23 minutes, so I'm going to pause right here and I'll be right back.